5,000 light-years away, a dying star is doing something that should be impossible. It has made a spot colder than empty space, colder than the leftover glow of the Big Bang. Scientists call it the coldest place in the universe, and the closer they look, the stranger it gets. We will visit a star that swallowed its partner, a cloud that drinks starlight, and a cosmic freezer racing toward absolute zero. If wonders like this pull you in, hit like and subscribe. Now hold still. We begin. Most people think cold is a thing, a force, something that creeps in through a cracked window or seeps through your jacket. Scientists found out something stranger. Cold has no substance. It carries no weight. Cold is an absence, the absence of heat, and heat is just atoms moving. Right now, every object around you is vibrating. The chair, the floor, your own hands, atoms. Inside, every object bounce and spin and crash into each other millions of times every second. You feel that motion as warmth. When things cool down, the atoms slow. When something gets extremely cold, the atoms slow, almost to a crawl. Here is the part that stops physicists in their tracks. Temperature is a measure of how fast atoms move. So somewhere at the very bottom of all temperatures, there is a point where atoms would stop moving completely. Scientists call it absolute zero. Absolute zero sits at negative 459 degrees Fahrenheit. To give that some weight, the coldest winter ever recorded on Earth was around negative 140 degrees Fahrenheit. Absolute zero is 3 times colder than that. Your freezer at home runs at about 0 degrees Fahrenheit. Absolute zero is 459 degrees beyond that. Picture a scale from the hottest thing in the universe, which is the surface of certain supermassive stars, all the way down to the absolute bottom. The entire scale of heat that everything in the universe can possibly have stretches across millions of degrees. Absolute zero sits at the very basement floor of that scale. One single step below it is physically impossible. The laws of physics themselves draw the line there. Scientists call this scale the Kelvin scale, named after a British physicist who worked out the math in the 1800s. On that scale, absolute zero is simply zero. Water freezes at 273. The surface of our sun sits at around 5,700, and the coldest possible temperature is zero. Full stop. Now here is the strange part. Every object in the universe, no matter how cold it looks in space, still holds some heat. Stars, yes, but also rocks floating in the dark between galaxies. Even the empty space between planets and stars carries a faint background warmth, a leftover glow from the earliest moments of the universe. Space is cold, but not perfectly cold. Scientists have chased absolute zero for over a century. Entire labs have been built with one goal: get as close to zero as possible. Chill atoms down until they barely whisper. Every fraction of a degree closer reveals new physics, new behavior. Things matter does at extreme cold that it does nowhere else. And yet, despite all the technology, all the liquid helium and magnetic traps and laser beams pointed at clouds of atoms in vacuum chambers, nobody has ever reached zero. Nobody has gotten there in a lab. No planet has gotten there. No dead star has gotten there. Until scientists pointed their telescope at a specific spot in the sky, 5,000 light-years from Earth. Something out there crossed a line that should be uncrossable. Something in space got closer to absolute zero than anything humans have ever built. And the closer scientists looked, the more they realized it was doing something that defied their models entirely. The story of how we found it starts with something you would never expect: a shape. There is a law in physics so firm that breaking it would unravel the entire universe. Physicists call it the third law of thermodynamics. And what it says is simple: you can never reach absolute zero. You can get close. You can get extremely, almost embarrassingly close. But zero itself stays just out of reach, forever. Here is why. To cool something down, you have to remove heat from it. You strip away the energy from its atoms. But every step of that process requires energy going somewhere. Heat moves from hot to cold. To keep cooling an object, you need something even colder surrounding it to pull the heat away. As you approach absolute zero, the differences get smaller and smaller. The steps get tinier. Each fraction of a degree costs more effort than the last. And as you approach zero exactly, the energy you would need to remove the final traces of heat becomes infinite. An infinite amount of energy to reach one temperature. The universe does not offer infinite resources, so zero stays locked behind a wall that no force in existence can knock down. Think of it like this. Imagine draining a swimming pool. You start with a pump and the water rushes out fast. Then it slows. As the water level drops, the pump has to work harder to pull out less and less water. By the time there is just a thin film on the floor, the pump is straining for almost nothing. Now imagine the pool gets infinitely harder to drain as it empties. You would never fully empty it. That is what cooling down toward absolute zero feels like for physicists. This is one reason scientists are so obsessed with getting close. Every step toward zero is harder than the last. Every fraction of a degree is a victory earned by brilliant engineering. Labs have cooled small clouds of atoms to fractions of a degree above zero that would have been unimaginable a generation ago. And each time, the atoms started doing something strange. Matter near absolute zero stops behaving the way everyday physics predicts. But here is the piece that stunned scientists when they first discovered it. While human labs were fighting to approach zero from above, spending billions of dollars and decades of work to get within a tiny fraction of a degree, something in deep space had done it on its own. No lab, no lasers, no magnetic traps, just a dying star, a cloud of gas, and a set of conditions so rare that scientists had never seen anything like it before. The object out there reached within 1 degree of absolute zero, 1 single degree above the floor. A natural object, sitting in space, colder than our best labs had ever achieved at the time of its discovery. When the team that found it ran the numbers a second time, they thought the instruments were broken. Then they ran them a third time. The readings held. Something in our galaxy had cracked open a door that physics says should stay shut. And the strangest detail? The universe's own background temperature, the faint warmth left over from the Big Bang that fills all of space, sits at roughly 2.7 degrees above absolute zero. This object was colder than that, colder than the universe's baseline temperature. It was pulling heat out of space itself. But to understand how that is even possible, you first need to understand what the leftover warmth of the Big Bang actually is. Because that warmth is stranger than it sounds. Empty space feels like it should be the coldest thing there is. No air, no wind, no friction. Just darkness stretching in every direction for trillions of miles. But space carries a temperature, a real, measurable temperature. And the reason it does reaches back to the very first seconds of the universe. About 13.8 billion years ago, all the matter and energy in existence was packed into a single point smaller than the tip of a pin. Then it expanded, fast and hot and in every direction at once. The early universe was a sea of plasma, a churning mix of particles and energy so dense and so hot that light itself could not travel through it. Photons, the tiny packets of light, kept crashing into matter before they could go anywhere. Then, about 380,000 years after the expansion began, the universe cooled just enough. Electrons settled into atoms, and for the first time, light broke free. It streamed outward in every direction across the whole universe. That light never stopped traveling. It has been crossing space for almost 14 billion years, and as the universe expanded, it stretched that light. The wavelengths grew longer, the energy faded. The light cooled from a blazing fireball into a faint, cold hum of microwave radiation that fills every corner of the universe today. Scientists call it the cosmic microwave background. It is the afterglow of the universe's first flash of light. If you could see microwaves, the entire sky would glow faintly in every direction, perfectly even, a soft signal from the beginning of time. The temperature of that glow is 2.7 degrees above absolute zero. Every point in space, every dark patch between galaxies, every void between stars carries that exact background temperature. It is the universe's flaw, the minimum warmth that space itself holds simply because of its own history. For a long time, scientists assumed nothing natural could be colder than that. The background radiation soaks into everything. It heats whatever it touches, even if just by a tiny fraction. Any object floating in space absorbs some of that background warmth and warms up slightly. That meant the 2.7 degree background was a kind of natural cold limit, a cosmic room temperature you could never cool below without extraordinary effort. Then they found the cloud that breaks the rule. One object in our galaxy sits at 1 degree above absolute zero. The cosmic background fills space around it at 2.7 degrees, so the background itself is warmer than the object. The warmth of the background should be flowing into the cloud, heating it up. The object should be warming, not staying cold. Instead, the cloud absorbs that background radiation. It drinks it. The cold cloud actually swallows the background warmth and pulls it in, which is how scientists proved it was colder. They could see the shadow it cast in the cosmic microwave background, a dark patch, a cold spot eating the universe's ambient heat. Nothing else in known space does this. Every other object either matches the background or runs warmer. This cloud breaks the rule, and scientists did not even know it existed until a telescope in Australia, on a quiet night in 1980, accidentally caught a glimpse of something shaped like a boomerang. What they thought they had found that night, and what it turned out to really be, could not have been more different. In 1980, two astronomers named Keith Taylor and Mike Scarrett were working at an observatory in the hills of New South Wales, Australia. The observatory sat at a place called Siding Spring Mountain, a dark stretch of sky far from city lights. They were surveying faint objects in the southern sky, the kind of routine cataloguing work that rarely makes headlines. They pointed their telescope at a faint smudge in the constellation Centaurus and took a careful look. What came back was unusual. The object had a shape, a gentle, curved outline. It reminded them of a boomerang, so they called it the Boomerang Nebula and wrote it into their records. A nebula is a cloud of gas and dust in space. There are thousands of them. Many are beautiful. Some are enormous. Most are well understood. Astronomers at the time assumed this was another one of those. A cloud left behind by some dying star, slowly spreading out into the dark. Nothing especially surprising. For years, the Boomerang Nebula sat in catalogues, referenced, photographed occasionally, largely forgotten. Then, in 1995, a scientist named Raghvendra Sahai got curious. He had been thinking about the physics of clouds around dying stars. He had published a paper 5 years earlier suggesting that some of these clouds might be far colder than anyone expected. The math worked out. If a cloud of gas was expanding fast enough, it would cool to dramatic temperatures. He needed a target to test the idea. The Boomerang Nebula looked promising. Sahai and his colleague Lars Ake Nyman pointed a large radio telescope at the cloud. Radio telescopes do not take pictures the way optical telescopes do. They detect radio waves coming from objects in space, and different atoms and molecules give off specific radio signals at specific temperatures. By reading the signals, scientists can measure temperature with precision. They aimed at the cloud. The signals came in. They ran the numbers. Then they ran them again. The cloud was radiating at a temperature close to absolute zero, 1 degree above it, colder than the cosmic background, colder than anything anyone had measured in space before, colder than the best refrigeration labs of the era had achieved with years of specialized equipment. They sat with those numbers for a while. What Taylor and Scarrett had stumbled onto 15 years earlier was not just another cloud in another catalogue. It was the coldest natural object in the known universe, the most extreme refrigerator that physics has produced without human hands. and it was sitting quietly in our own galaxy, 5,000 light-years away, waiting for someone to take a temperature reading. But calling it the coldest place in space was only the beginning, because when scientists started asking why it was so cold, the answers started getting strange. The cloud was doing things a single dying star should not be capable of doing. The temperatures were too extreme, the speeds were too fast, the amount of material thrown out was too large. Something unusual had happened at the heart of that cloud, something violent enough to break the expected patterns of stellar death. And it had happened relatively recently in cosmic terms. What caused it would take another 22 years to figure out. And the answer, when it finally came, changed the way scientists think about how stars die. 1995 was a good year for astronomy. Scientists were discovering planets around other stars for the first time. The Hubble Space Telescope was delivering some of its first sharp images. The scientific community was buzzing. And then, out of a radio telescope in Chile, came a reading so strange it stopped people mid-sentence. Sahai and Nyman published their findings. The Boomerang Nebula, the forgotten boomerang-shaped cloud from 15 years earlier, had a temperature of 1 degree above absolute zero. Written out on paper, that number sat on the page and confused people. Here is the scale that matters. Absolute zero is the floor. The universe's own background temperature is 2.7 degrees above that floor. Every point in empty space, every dark corridor between galaxies, carries that much warmth just from the afterglow of the Big Bang. 2.7 degrees was considered the coldest that space itself gets. The Boomerang Nebula registered at 1 degree. That meant it was colder than the universe's ambient temperature by almost 2 full degrees. The background radiation that fills all of space should be warming it, but the cloud was running colder than the warming agent itself. And when scientists looked at the data more carefully, they realized the cloud was actually absorbing the background radiation. It was swallowing the warmth of space around it and pulling it in. This had never been observed anywhere before. No other natural object in the known universe had been found to sit below the temperature of the cosmic background. The Boomerang Nebula was the only one, and that made it something genuinely new in the catalogue of space. The scientific community took notice. Teams tried to find errors in the data. They checked the instruments. They looked for alternative explanations. Was the cloud being confused with something else? Were the radio signals being misread? Could nearby interference have skewed the temperature reading? Every check confirmed the result. The cloud was real. The cold was real. What made it even stranger was the location. The Boomerang Nebula is inside our own galaxy, the Milky Way. 5,000 light-years is a significant distance. If you could travel at the speed of light, it would take you 5,000 years to get there. But on a galactic scale, it is practically in our backyard. The Milky Way stretches about 100,000 light-years across. This record-breaking cold spot sits within 5% of our galaxy's width, relatively close. Something in our own cosmic neighborhood had beaten the laws of thermal physics, and astronomers began asking the question that would drive research for the next 2 decades. How? A dying star, doing what dying stars do, should cool to the background temperature. It should not overshoot it. It should not keep going. There had to be a mechanism. Something had to be pulling heat out of the cloud at an extraordinary rate. The first clue came from the speed of the gas. The cloud was moving outward at around 360,000 miles an hour. That is fast, extremely fast. Fast enough that the expansion itself was bleeding heat out of the gas, faster than the surrounding universe could replace it, like a pressure valve releasing so much at once that the system goes far colder than it should. But 360,000 miles an hour raised a new problem. That was far too fast for one dying star to produce. Something else had to be involved. 5,000 light-years. Scientists say that number and move on quickly because it fits neatly into a sentence. But that number deserves a moment, because 5,000 light-years is a distance so enormous that no human tool ever built can cross it, and no human alive will ever get close to it. Start with what a light year actually is. Light travels at about 186,000 miles per second. In 1 second, light could circle the Earth 7.5 times. In 1 minute, light travels about 11 million miles. In 1 year, at that speed, light covers roughly 5.9 trillion miles. 5,000 light years is 5,000 times that distance. If you wrote out the full number in miles, it would stretch across this page and several others. It is a distance so vast that numbers stop carrying meaning after a while. Here is a way to feel it. Our nearest neighboring star is about 4 light years from Earth. If you launched a spacecraft today, at the fastest speed any human vehicle has ever traveled, about 40,000 miles an hour, it would take about 70,000 years to reach that nearest star. 4 light years, 70,000 years. The Boomerang Nebula is 5,000 light years away. By that same math, it would take you close to 87 million years to reach it in our fastest spacecraft. The earliest humans walked the Earth less than 300,000 years ago. Our entire recorded history covers roughly 5,000 years. That trip would take 17,000 times longer than everything humans have ever done combined. And yet, with radio telescopes, scientists can measure its temperature from Earth. They can detect the specific signals its atoms give off, read the wavelengths, and calculate the heat of a cloud. Sitting at a distance, our minds cannot fully hold. There is something about that fact that shifts the way space feels. The universe hides its secrets at scales that make travel impossible, but it lets light and radio waves carry the answers. Science runs on those signals. Every discovery about distant objects comes from reading the light, or the radio waves, or the microwaves that travel across those incomprehensible distances and arrive here at Earth. The Boomerang Nebula sits in the constellation Centaurus, a patch of sky visible from the southern hemisphere. From the ground with the naked eye, you see nothing there. Even with a basic telescope, the smudge is faint, easy to overlook. The detail inside it, the shape of the gas, the temperature gradients, the inner structure, only appeared when scientists used powerful radio telescopes to pull apart the signals. And what those signals revealed, over several decades of study, was a structure unlike anything else in the catalogue of known nebulae. A bow-tie shape, 2 lobes, spreading out from a dying star at the center, expanding so fast the gas was cooling to temperatures the universe barely allows. The Boomerang Nebula is small on a cosmic scale, just a few light years across, surrounded by the galaxy in every direction. But inside that small volume, conditions have developed that have no match anywhere else in the observable universe. Something extraordinary had to create them. And to understand what that something was, you first have to understand what the cloud actually is. What kind of object? What type of star? What phase of death produces a structure like this? The answer brings you face to face with the end of a star, and eventually, the end of our own Sunday. The Boomerang Nebula is a star's final gasp, a dramatic, violent, freezing final gasp. To understand what is happening inside the cloud, you need to follow the life of the star at its center. It started its life like most stars do, a ball of gas pulled together by gravity, slowly heating up until the pressure at its core became high enough to start nuclear fusion. Hydrogen atoms began slamming together at the center, fusing into helium, releasing enormous energy. That energy pushed outward against gravity and held the star in balance. Our own sun is doing this right now, has been doing it for about 4.5 billion years. We'll continue doing it for roughly another 5 billion. Then things change. When a star like this burns through most of its hydrogen fuel, the core begins to shrink. As it shrinks, it heats up. That extra heat pushes the outer layers of the star outward. The star swells. It becomes a red giant, a bloated version of its former self, expanding to perhaps 100 times its original size. A star that was once compact becomes enormous and relatively cool at its surface. But the star is still using up fuel. The helium in the core starts fusing. Eventually, a star with a mass similar to our Sun cannot fuse anything heavier. The fusion slows, the balance breaks, the core begins to collapse, while the outer layers get pushed away. This is the stage called the planetary nebula phase. The outer layers of the star are pushed out into a shell of gas and dust around the collapsing core. The core itself shrinks into something dense and white-hot called a white dwarf. The cloud of gas and dust around it catches ultraviolet light from the hot core and glows. Planetary nebulae are some of the most beautiful objects in space. They come in rings and bubbles and spirals. They spread out over light years, and eventually they fade, mixing with the gas between stars. The Boomerang Nebula is in the stage just before this. Scientists call it a preplanetary nebula. The outer layers have started moving outward, but the central star has not yet become hot enough to make the gas glow brightly. The cloud is expanding, the gas is spreading, and for reasons scientists spent decades trying to understand, it is expanding at a speed far beyond what any single dying star should produce. A typical star in this phase throws gas outward at around 15 miles per second. That is already fast. The Boomerang Nebula's gas is moving at roughly 100 miles per second, almost 7 times faster. The scale of that difference matters. Velocity drives cooling. The faster the gas expands, the more rapidly its temperature drops. The same physical principle that makes the liquid inside an aerosol can feel cold when you release the pressure. The gas expands and cools. At 100 miles per second of expansion, the gas drops to temperatures far beyond what models for single dying stars could explain. Scientists knew from the start that something unusual was powering the outflow. They just did not know what. The star at the center carries the answer, but it took more than 2 decades and a new generation of telescopes to look closely enough to find it. In 1995, years before anyone confirmed the Boomerang Nebula's temperature, a scientist at NASA's Jet Propulsion Laboratory published a quiet paper. It did not make headlines. It sat in a journal and drew a modest amount of attention. But inside that paper was a prediction that would turn out to be exactly right. Raghvendra Sahai was thinking about clouds around dying stars. He was working through the physics of what happens when a star sheds its outer layers quickly. Gas pushed outward from a stellar core expands as it moves, and expanding gas cools. Every atmospheric physicist and every engineer who works with pressurized systems knows this. Compress gas, it heats. Let it expand freely, it cools. Sahai worked the numbers. He calculated what would happen if the gas around certain dying stars was expanding fast enough. The cooling rate would be dramatic. The temperature could drop far below anything previously documented in space. He suggested that some of these dying star clouds might reach temperatures close to absolute zero. Nobody went looking for them right away. The prediction lived in the paper. Life moved on. Observatories kept busy with other targets. Then Sahai and Nyman pointed their telescope at the Boomerang Nebula in 1995 and found exactly what the paper had predicted. The cloud was at 1 degree above absolute zero. Sahai had written the math 5 years earlier. The universe had been holding the answer the whole time, waiting for the right telescope to ask the question. This kind of thing matters in science. The most powerful discoveries usually come in 2 steps. First, a scientist builds a model, works through the mathematics, and makes a prediction. Then, either that scientist or someone else goes looking for the evidence. When the evidence matches the prediction, something clicks into place. The model was right. The physics holds. Sahai's prediction and its confirmation gave scientists a new category: cold stellar outflows. Preplanetary nebulae that expand fast enough to dramatically overshoot the background temperature of the universe. The Boomerang Nebula was the first confirmed example, and its discovery opened a new direction of research into how stars shed mass as they die. But the confirmation in 1995 was only the first layer. The temperature reading was real. The cloud was genuinely cold. The expansion speed was genuinely unusual. But the deeper question stayed open for a long time. What was powering the outflow? Why was the gas moving so fast? Sahai kept working. He returned to the nebula with better instruments. He and other teams applied for telescope time and looked at the cloud from new angles and at new wavelengths. Every new look revealed more structure. The cloud was larger than first thought. The mass of gas in the outflow was enormous. The energy required to produce that outflow at that speed was far beyond what models for single dying stars could provide. Something in the center of that cloud had added extraordinary energy to the system, something that single star models could not account for. And as telescope technology improved, the picture at the center of the cloud started to get clearer. What it showed would eventually change how scientists think about the death of stars across the galaxy. But before getting there, you need to understand the mechanism behind the cold itself, and why the same physics that cools down the spray from an aerosol can was working out in space at a scale millions of times larger. Here is something you can test the next time you find a can of compressed air, the kind used to clean keyboards. Hold the can upright and spray for a few seconds. Now, touch the metal side of the can. It feels cold, sometimes noticeably cold, even on a warm day. You did not add cold to the can. You removed pressure. The gas inside was compressed. When it released and expanded rapidly into the open air, its temperature dropped. The atoms in the gas spread out, moving faster and hitting each other less often. With fewer collisions, the average energy per atom drops. Temperature drops. This is one of the fundamental behaviors of gas. Physicists call it adiabatic cooling. It is the same process that makes air cooler at high altitude, where atmospheric pressure is lower. It is the same process that runs inside your refrigerator, where a coolant gas expands and absorbs heat from the inside of the fridge. It is the same process at work inside the Boomerang Nebula, at a scale that makes every refrigerator on Earth look like a novelty toy. The dying star at the center of the nebula is pushing gas outward. That gas starts densely packed near the star. As it travels outward, it spreads into a larger and larger volume. The pressure drops, and as the pressure drops, the temperature follows it down. The key ingredient is speed. The faster the gas expands, the faster the cooling happens. A slow expansion gives surrounding heat time to leak back in and warm the gas. A fast expansion outpaces that warming. The gas drops before anything can catch it. The Boomerang Nebula's gas is moving outward at close to 100 miles per second. To put that in perspective, a bullet from a high-powered rifle travels about half a mile per second. The gas in this nebula is moving 200 times faster than a bullet, outward in all directions, from a dying star at the center. At those speeds, the expansion is essentially instantaneous on any human timescale. The gas shoots outward, pressure collapses, temperature follows it down, and because the expansion is so fast and so sustained, the gas drops below 1 degree above absolute zero before the surrounding universe can warm it back up. And the surrounding universe keeps trying. The cosmic microwave background, the faint warmth of the Big Bang's afterglow, is always there. It presses in from every direction. Normally, any cloud of gas in space would absorb that warmth and eventually come to the same temperature as the background. The Boomerang Nebula's gas is expanding faster than that warmth can be absorbed. The cooling is winning. That is why the cloud is colder than the background. The gas is sprinting away from equilibrium so fast that the universe cannot catch up. Now here is the problem. The math works beautifully for the cooling rate. Expand gas fast enough, it gets cold enough. That checks out. But when scientists calculated how much gas was in the cloud and how fast it was moving, and worked backward to figure out how much energy it took to produce that outflow, the numbers came up too large. One dying star, doing what dying stars do, could not put that much gas in motion at those speeds. The energy budget did not balance. Something else had to be powering the explosion. and when scientists finally found it, the answer involved a second star that nobody had been looking for. 1 degree above absolute zero. Written out that way, it sounds like a small gap. Almost there, just one step from the bottom. But that framing undersells what that number actually means in physical terms. At room temperature, the atoms in the air around you are moving at roughly 1,000 miles an hour. They are vibrating, bouncing off each other, crashing into walls and surfaces millions of times every second. That constant chaotic motion is what heat is. Bring the temperature down toward absolute zero, and those atoms slow. At the temperature of liquid nitrogen, which is used to freeze things almost instantly in laboratories, atoms are moving significantly slower. At the temperature of liquid helium, used to cool medical scanners and particle accelerators, the atoms slow further still. Scientists have to work extremely hard just to reach liquid helium temperatures. Special equipment, specialized facilities, years of engineering refinement. At 1 degree above absolute zero, the atoms are barely moving. The thermal energy left in the system is almost nothing. Each atom holds almost no kinetic energy at all. The motion is a whisper. To reach 1 degree above absolute zero in a laboratory in 1995, when the Boomerang Nebula's temperature was first confirmed, would have required extraordinarily specialized equipment. Dilution refrigerators, magnetic traps, laser cooling, the kind of hardware you find in advanced physics labs at major research universities, not something assembled casually. The Boomerang Nebula reached that temperature without any of that. No lasers, no magnets, no refrigeration pumps, just the physics of expanding gas, working at a scale that covers a volume of space larger than the distance between our Sun and our nearest stellar neighbor. The cold region of the Boomerang Nebula spans an area roughly 1 light-year across. 1 light-year is about 6 trillion miles. Picture a sphere 6 trillion miles in diameter, filled with gas sitting at 1 degree above absolute zero. That is not a small cold spot created in a vacuum chamber the size of a filing cabinet. That is a cold zone large enough to hold thousands of solar systems. And it holds that temperature across that entire region. The cooling effect is consistent. Not a pocket here and there, but a sustained, enormous envelope of near absolute zero gas drifting in space. There is a detail buried in the measurements that made scientists stop and reconsider. The temperature reading is not exactly 1 degree. It is slightly below 1, closer to 1 Kelvin, and in some regions, perhaps lower. Later observations with more precise instruments placed some sections of the outflow at below 0.5 degree above absolute zero. 0.5 degree. Less than the thickness of a single step on the temperature scale above the very bottom. No natural object in the universe had been found at that temperature before. The record had been held by labs on Earth, by precision experiments with specialized equipment. A dying star's outflow in deep space had matched or beaten those records. And then came the detail that made the temperature readings even stranger. When scientists measured the cloud against the background radiation of the universe, they found the cloud was not just cold, it was actively drinking the warmth around it. What that means for the physics, and how scientists confirmed it, is where the story gets genuinely strange. Science runs on evidence. A temperature reading from a single instrument on a single night could have errors, calibration problems, interference from other sources. Scientists needed a way to confirm the Boomerang Nebula's temperature that did not rely solely on one set of measurements. The confirmation came from the cosmic microwave background itself. The cosmic microwave background is the faint glow of radiation left over from the Big Bang. It fills all of space evenly. Every direction in the sky carries this background warmth at the same temperature, roughly 2.7 degrees above absolute zero. Satellites have mapped it in extraordinary detail. It is one of the most precisely measured things in all of physics. Here is the key property. When this background radiation travels through a region of gas, one of two things can happen. If the gas is warmer than the background, the gas adds energy to the radiation and the signal comes out brighter in that direction. If the gas is colder than the background, the gas absorbs some of the radiation and the signal comes out dimmer. A cold cloud creates a shadow in the background glow. This effect is called the Sunyaev-Zeldovich effect in other contexts, but the basic principle is simpler than the name suggests. Cold things absorb warmth from their surroundings. Hot things radiate warmth outward. If you look at the cosmic microwave background through a patch of cold gas, that patch will appear darker because the gas is pulling some of the background radiation in rather than letting it pass through. When scientists looked at the Boomerang Nebula against the cosmic microwave background, they saw a dark spot. Not because there was nothing there, but because the cloud was absorbing the background radiation behind it. The cloud was so cold that the microwave background was flowing into it like heat flowing into a block of ice. This was the proof. The temperature reading from the radio telescope said 1 degree above absolute zero. The dark shadow in the cosmic microwave background confirmed it independently. Two different measurement methods, two different physical effects, both pointing to the same conclusion. The cloud was colder than the universe's own background temperature. The Boomerang Nebula became the only known object in the universe confirmed to sit below the cosmic microwave background temperature. Every other natural object in space, every star, every planet, every cloud of gas, every dust cloud, sits at or above 2.7 degrees. One small region of our galaxy, a few light years across, sits below it. Scientists described the cloud as a cosmic refrigerator. The phrase caught on, and it was accurate. A refrigerator pulls heat away from its interior and dumps it outside. The Boomerang Nebula's rapid gas expansion is pulling heat away from the cloud continuously, faster than the surrounding universe can replace it, creating a sustained cold spot that defies the thermal equilibrium of space. But here is the piece that sat unresolved. The refrigerator needs power to run. A kitchen refrigerator uses electricity. The Boomerang Nebula's refrigerator uses the energy of the outflow, the kinetic energy of all that gas moving outward at extreme speed, and the amount of energy in that outflow was enormous, far larger than scientists expected from a single dying star. The power source behind the outflow was hiding at the center of the cloud, and it was stranger than any model had predicted. The gas coming out of the Boomerang Nebula is moving fast. The numbers confirm it, but there is a second kind of outflow inside the nebula that makes the main gas cloud look slow. A wind from the dying star at the center, blowing outward at speeds that put most things in the solar system to shame. Scientists measured the stellar wind coming from the central star of the Boomerang Nebula. It clocks in at roughly 360,000 miles an hour. For comparison, the solar wind from our own sun, the constant stream of charged particles that flows outward from it, travels at roughly 1 million miles per hour at its fastest. But the particles in our sun's wind are extremely thin, spread across an enormous area. The Boomerang Nebula's wind is denser, more sustained, and is pushing enormous volumes of material outward. To picture the force involved, think of standing in front of an industrial fan the size of a city, pointed at you, running continuously for 1,500 years. That is roughly how long scientists estimate the current outflow phase has been active. 1,500 years of sustained wind at those speeds, pushing gas and dust outward in a steady, expanding shell. In that 1,500 years, the star has thrown off material equivalent to roughly 1,000th of the sun's total mass per year. 1,000th sounds small, but the sun is enormous. 1,000th of its total mass per year, sustained for 1,500 years, adds up to a colossal amount of matter dispersed into space. Scientists comparing this to similar objects found that the Boomerang Nebula was losing mass between 10 and 100 times faster than comparable dying stars. Standard models of stellar mass loss could not account for that rate. A normal red giant star in this phase sheds its outer layers gradually, over thousands to tens of thousands of years, at much lower speeds. The Boomerang Nebula was doing it faster and harder. The combination of factors was unusual enough that scientists flagged it early. The speed was too high, the mass loss rate was too high, the temperature was too low, Each individual measurement could have had an explanation on its own. Together, they pointed towards something anomalous happening at the center of the cloud. The shape of the nebula added to the puzzle. The two lobes extending outward, the bow tie structure that gave the nebula its original name, were more symmetric and more elongated than most objects of this type. Most dying star clouds are roughly spherical. Gas moves outward in all directions from the central star, creating a bubble or shell. The Boomerang Nebula's gas was concentrated along a specific axis, flowing out more strongly in two opposite directions. That kind of shaping usually requires a force beyond a single spherical star. Binary stars, two stars orbiting each other, often produce asymmetric outflows because the gravity of one star shapes the gas coming from the other. The shape of the Boomerang Nebula was hinting at a second object, something at the center influencing the direction and power of the outflow. But in the observations available at the time, scientists could not directly see a companion star. The center of the cloud was obscured by the gas itself. Whatever was there stayed hidden. The mystery was clear. The answer was not, and it would stay that way for more than 2 decades. By the early 2000s, the Boomerang Nebula had been studied enough for scientists to map out the problem cleanly. It was not one confusing measurement. It was a cluster of things that all pointed to the same conclusion. A single dying star could not have done this. Here is the case against the single star explanation built from the evidence. A typical dying star in this phase pushes gas outward at around 15 miles per second. The Boomerang Nebula's gas is moving at roughly 100 miles per second. That is almost 7 times faster. In a simple expanding gas model, the kinetic energy, the energy of motion, increases with the square of velocity. 7 times faster means roughly 49 times more energy in the outflow. A single star's output simply does not scale that far. The mass in the outflow made it worse. Scientists calculated the total mass of gas in the cold, expanding cloud. It came out at more than 3 times the mass of our Sunday. The star at the center had to have expelled that entire mass from its outer layers into space. But the star, as observed, had a mass of roughly 4 times the Sunday. If the cloud contains 3 solar masses of expelled material, the star has lost most of itself, and it lost that material in a relatively short time, between 1,000 and 1,500 years on current estimates. 1,000 years sounds like a long time in human terms. In stellar terms, it is a blink. Stars live for billions of years. Shedding 3 solar masses of material in 1,000 years is an extraordinary rate. Standard models of red giant mass loss cannot produce it. The energy budget was the final piece. Scientists calculated how much kinetic energy was needed to explain the outflow. The mass of the gas times the velocity squared, divided by 2. The result was a number so large that feeding it into models of single dying stars produced a clear mismatch. A single star's envelope does not carry that much energy available for expulsion. The shape of the outflow told the same story. A single star expelling gas in all directions should produce a roughly symmetric cloud. The Boomerang Nebula has a pronounced 2-lobe structure. The gas streams out more strongly along one axis. This kind of geometry regularly shows up in systems where 2 bodies are interacting. Binary stars shape each other's mass loss. The gravity of one distorts the outflow from the other. The elongated bow tie shape of the cloud was consistent with binary star activity. Every line of evidence pushed in the same direction. Something beyond a single dying star was driving the outflow. The temperature was too low, the speed was too high, the mass expelled was too large, the energy required was too great, and the shape was too asymmetric. Scientists had their answer. In broad terms, by the mid-2000s, a companion star was almost certainly involved, but confirming it required seeing inside the cloud. Optical telescopes could not penetrate the thick gas and dust at the center of the nebula. The obscured core kept it secret. The tool that finally unlocked it was a new kind of telescope, one that could see through the gas using radio waves. map the structure of the cloud in detail, and measure its properties with enough precision to confirm or rule out theories. That telescope sat on a high desert plateau in South America, and when it turned its attention to the Boomerang Nebula in 2013, it started revealing things no one had seen before. Between 1995 and 2017, the Boomerang Nebula sat in a strange position in astronomy, famous enough to appear in lists of record-breaking space objects, cold enough to be genuinely remarkable, but unexplained enough that every new observation raised more questions than it answered. The core problem was the obscured center. The thick cloud of gas and dust that made the nebula cold also blocked direct views of the star system driving it. Optical telescopes, the kind that detect visible light, could not see through that shroud. Scientists could measure the properties of the outer cloud. They could track the temperature, the velocity of the gas, the shape of the lobes, the total mass of the expelled material. But the engine at the center stayed hidden. So the mystery split into two parts. The first was the cold itself. The second was what caused it. The cold was confirmed by multiple observations over the years. Different telescopes, different methods, different teams, all returned the same result: 1 degree above absolute zero. The cloud absorbing the cosmic microwave background. The dark spot in the background glow. The temperature was real, verified repeatedly, and entirely without precedent in the natural universe. The cause was where debate continued. The binary star hypothesis, the idea that a companion star had interacted with the central dying star, was the leading explanation by the early 2000s. The energy numbers, the mass numbers, the shape of the cloud all pointed toward it, but no one could directly confirm it. The companion star, if it existed, was hidden inside the dense cloud at the center. Other explanations were floated. Could the star have experienced some unusual internal process that drove extra mass loss? Could there be a massive planet involved? A giant body orbiting the dying star and gradually spiraling inward? Could the outflow be powered by a rapidly spinning stellar core, a type of engine called a magnetar or a fast rotator? Each suggestion got examined. Each fell short of explaining all the observations together. The binary star hypothesis kept winning. It explained the most with the fewest additional assumptions. But winning an argument and proving something are different things. Science requires evidence. 22 years passed. The Boomerang Nebula stayed on lists of unsolved mysteries. Graduate students wrote theses about it. Review papers included it as an open case. Astronomers submitted proposals for new observation campaigns. The nebula waited in the sky, holding its cold, its speed, its unexplained energy, its shrouded center. And then, in 2013, a telescope array called the Atacama Large Millimeter Array came online in the Atacama Desert of Chile. It sat at an altitude of about 16,000 feet, above most of the atmospheric water vapor that interferes with certain wavelengths of radio observation. It used an array of 66 separate dishes working together to achieve resolution sharp enough to see fine structure in distant objects. For the first time, scientists could look at the Boomerang Nebula not just as a cloud with measurable average properties, but as a structure with internal detail. They could map the temperature gradients, the velocity patterns, the distribution of mass, and the core region in far more detail than any previous telescope had allowed. What those observations showed changed the picture of what had happened at the center of the cloud, and when the full results were published in 2017, the wait turned out to have been worth it. In 2017, a team led by Raghavendra Sahai published new results based on observations from the Atacama Large Millimeter Array. These were the most detailed measurements of the Boomerang Nebula ever taken. The paper appeared in the Astrophysical Journal and answered the question that had been sitting open since 1995. The conclusion: a companion star almost certainly plunged into the core of the dying red giant. Here is what the evidence showed. The total mass of the cold outflow came in at more than 3 solar masses. The kinetic energy in that outflow, The energy of all that gas moving at close to 100 miles per second required an input far beyond what the star's outer envelope could provide on its own. When scientists calculated the energy needed, only one source could supply it: the gravitational energy released by a companion star falling inward. Gravity is a powerful energy source. When a massive object falls toward another massive object, it releases energy. The further it falls and the more massive the objects involved, the more energy gets released. A star falling into the core of another star releases an amount of energy that dwarfs most other processes in astronomy. Sahai and his team calculated that the companion star, probably a star smaller than our Sun, had fallen into the outer layers of the red giant and spiraled inward. As it fell, it released gravitational energy. That energy drove the extraordinary outflow. The mass of the red giant's outer layers, energized by the infalling companion, got blasted outward at speeds no single star could produce. The outflow rate, 10 to 100 times higher than typical dying stars, now had an explanation. The speed of the gas, close to 7 times faster than normal, had an explanation. The total mass expelled, enough to account for most of the original star's outer layers, had an explanation. The asymmetric two-lobe shape, consistent with a binary system, had an explanation. Every anomaly that had puzzled scientists for 22 years fell into place under this single model. A companion star fell. The collision released energy. The energy drove the outflow. The outflow expanded fast. The expansion cooled the gas to record temperatures. The companion star itself was consumed. Scientists found evidence of a dusty disk at the center of the nebula, a disk of material that forms when a smaller star spirals into a larger one. This disk is a fingerprint of the merger event. It confirmed the collision had happened. The timing of the outflow, estimated at around 1500 years based on the current size and speed of the cloud, meant this event happened roughly 1500 years ago in the star's frame of time. The light carrying the evidence of that collision has been traveling toward Earth for 5,000 years. Humans did not have telescopes pointed at that patch of sky when the event happened, but the signals eventually arrived, and decades of careful observation pulled the story out of them. There was one part of the picture that the 2017 study revealed that surprised even the scientists involved. The nebula was bigger than previous observations had shown. The cold outflow extended to distances from the central star that had not been captured in earlier data, and at the edges of that extended outflow, something was changing. The central event of the Boomerang Nebula story is a merger. 2 stars became one, and in the process, the larger star turned its companion into the fuel that powered one of the most extreme cooling events in the known universe. To picture what happened, start with the 2 stars in their original state. The larger star, with a mass somewhere around 4 times the mass of our Sun, had been living out its life on the main sequence, fusing hydrogen at its core, stable and predictable for billions of years. The smaller companion, perhaps similar in mass to our Sun, or somewhat smaller, orbited it at a distance, 2 stars circling each other, locked in a gravitational dance. As the larger star aged, its hydrogen fuel ran low. The core shrank and heated. The outer layers expanded. The star became a red giant, and a red giant is enormous. A red giant version of our Sun would extend out past the orbit of Mercury, possibly past Venus. This star was already 4 times the mass of our Sun to begin with, so its red giant phase was correspondingly larger. As the red giant swelled, it swallowed the space between itself and its companion. The companion star, orbiting at some distance, eventually found itself inside the outer envelope of the giant. It was orbiting inside the star. That situation does not last long. The gas of the stellar envelope creates drag. The companion, moving through the thick outer layers of the giant, slowed down. As it slowed, its orbit shrank. A smaller orbit means faster movement, but the drag kept slowing it. The companion spiraled inward, closer and closer to the dense core. This process is called common envelope evolution in astronomical literature. It happens in binary star systems where one star expands to engulf its companion. The companion spirals in, the two cores interact. Enormous energy is released. In the Boomerang Nebula's case, the companion spiraled all the way into the core region and merged with it. The energy released in that final merger was staggering. Gravitational potential energy converted into kinetic energy and heat, all of it dumping into the outer layers of the giant. Those layers, already loosely bound to the core, got blasted outward. The velocity of that blast, close to 100 miles per second, reflects the energy of the merger. A single star shedding its layers gradually through normal wind processes moves gas at 15 miles per second. A star energized by a companion merger can achieve 6 or 7 times that speed because the energy input is dramatically larger. The companion star is gone now, absorbed, its mass merged with the central star's core. What remains is a single white dwarf in the making, the collapsed remnant of the two merged cores, surrounded by the enormous cloud of expelled gas that the merger sent outward. The cloud is the record of the collision. Every cubic mile of gas in the Boomerang Nebula's cold outflow carries the imprint of that ancient merger, and the temperature of that gas, 1 degree above absolute zero, is the direct result of the speed the merger gave it. 2 stars became one, the smaller one was consumed, and the collision turned the giant's outer layers into the coldest natural structure in the observable universe. But the story was still not finished. Because the nebula the merger created was doing something unexpected at its edges, something that changed scientists' understanding of how long the cold could last. When 2 stars merge, the energy released is enormous. But where does that energy go? It does not vanish. Energy in physics always goes somewhere. In the Boomerang Nebula's case, it went directly into the gas surrounding the merged cores, accelerating it outward at a speed that set records and drove temperatures down to near absolute zero. Normal stellar winds from dying red giants move at around 15 miles per second. This is the expected speed for a star losing its outer layers through the standard process. Radiation pressure from the hot core pushes gas outward. Pulsations in the star's outer layers drive additional mass away. The result is a slow, sustained wind that builds a shell of gas over thousands of years. The Boomerang Nebula's gas is moving at close to 100 miles per second. That is roughly 6 to 7 times faster than the typical stellar wind. And the reason that matters comes down to a simple relationship in physics. Kinetic energy increases with the square of speed. If you double the speed of something, it carries 4 times the energy. Triple the speed, 9 times the energy. 6 times faster means the gas in the Boomerang Nebula carries roughly 36 times more kinetic energy per unit of mass than gas from a typical dying star. 36 times. From the same type of star, in the same phase of death. That enormous energy input came from the merger. The companion star fell into the core of the red giant and released gravitational energy on a massive scale. That energy transferred into the outer envelope of the giant, accelerating it outward. The explosion was not a supernova, which destroys the entire star in seconds. It was a sustained, energetic blast of the outer layers, driven by the companion's infall, leaving the core intact. The scale of the energy became clear when scientists ran the full mass and velocity measurements from the 2017 observations. They calculated the total kinetic energy of the entire outflow. The number came out consistent with what you would expect from a companion star of around 1 solar mass falling into the core of a larger red giant. The gravitational energy released by that merger could account for the entire outflow's kinetic energy budget. It was a clean match. The theory fit the data. The merger was powerful enough to explain everything: the speed, the temperature, the mass, the shape, and the energy. And the speed was the linchpin. Because speed was what created the cold. Faster gas expands more rapidly. Rapid expansion drops the temperature faster then the surrounding universe can replace heat. The link from merger to companion, to speed, to expansion, to temperature was direct, each step following from the last. Scientists described the Boomerang Nebula as a system where a cosmic accident, two stars merging, produced a record-breaking physical outcome. The cold was a side effect of the violence, an accidental refrigerator built by a catastrophic event. But the 2017 study added one more finding that changed the long-term picture of the nebula. At the outer edges of the cold outflow, where the gas had been traveling the longest and spreading the thinnest, the temperatures were rising. The gas was warming back up, and the reason it was warming introduced a new element into the story, one that put a clock on how long the coldest place in the universe could hold its title. The Boomerang Nebula is not a small cloud. Scientists spent years measuring its full size, and every new measurement pushed the boundaries further outward than the last estimate. The initial observations in the 1990s gave a rough sense of the cloud's extent. It appeared to cover a few light years. That alone was impressive. But the detailed mapping done with the Atacama Large Millimeter Array, released through a series of studies in the 2010s, revealed a structure much larger than that. The cold outflow, the region of gas sitting below the temperature of the cosmic background, extended more than 120,000 times the distance between Earth and the Sun in every direction from the central star. To put that number in something you can feel, the distance from Earth to the Sun is about 93 million miles. Multiply that by 120,000. The cold zone of the Boomerang Nebula covers a volume measured in trillions upon trillions of miles. Inside that enormous region, the mass of gas is staggering. Scientists calculated the total mass in the ultra-cold outflow at more than 3 times the mass of the Sunday, 3 complete suns' worth of gas, dispersed into space by a single stellar system undergoing a catastrophic merger. That number reshapes how you see the nebula. The star at the center started with roughly 4 times the Sun's mass. It has expelled more than 3/4 of its material into space. What remains at the center is a dense, collapsing core, the embryo of a white dwarf. The outer layers of what was once a star, a body that burned for billions of years, have been scattered across an enormous volume of space. And that gas is cold, extremely cold. The entire 3 solar masses of expelled material, spread across an area bigger than most people can picture, sits at near absolute zero temperatures. The mass and the temperature together are what make the Boomerang Nebula genuinely unprecedented. Other nebulae have mass. Other objects have extreme temperatures. No other natural object combines that much mass with that lower temperature. The energy required to produce that outcome is where the merger explanation becomes essential. Moving 3 solar masses of gas to 100 miles per second requires a colossal input of kinetic energy. That energy had to come from somewhere. Single dying stars simply cannot budget it. The gravitational energy released by the companion star spiraling into the core could. The math closes only when the merger is included. What scientists also found in the detailed mapping was that the outflow was not uniform. The density varied. Some regions were thicker, some were thinner. The velocity varied too, with gas in the inner lobes moving somewhat faster than gas in the outer edges. This variation in structure pointed to the complex dynamics of the merger itself, a chaotic event that threw material outward in a slightly uneven pattern rather than a perfect sphere. The inner structure also revealed a disk of large, millimeter-sized dust grains sitting at the waist of the nebula, around the central star. That disk was what blocked starlight from escaping sideways and forced it to leak out in 2 narrow beams in opposite directions, creating the hourglass shape visible in optical telescopes. Every detail the new measurements revealed added texture to the picture, and one of those details, discovered at the outermost edges of the cold outflow, changed what scientists expected the nebula's future to look like. For 20 years after the initial discovery, the Boomerang Nebula was measured with single-dish radio telescopes. These instruments are powerful, but they operate like a camera with limited zoom. They measure the average properties of whatever falls inside their view. When pointed at the Boomerang Nebula, they returned an average temperature, an average velocity, a rough sense of the cloud's shape. The Atacama Large Millimeter Array changed everything about that picture. This telescope array uses dozens of individual dishes spread across the desert plateau, working together as a single instrument. By combining their signals, the dishes effectively act as one enormous telescope, many miles wide. This gives the array sharp resolution, sharp enough to resolve fine structure inside the cloud rather than just averaging across it. When the array mapped the Boomerang Nebula in detail for the first time, scientists found the cold zone extended far further than previous measurements had suggested. The prior instruments had missed the outermost regions of the outflow. Those outer regions, too thin and too diffuse for single-dish telescopes to detect reliably, turned out to be substantial. The true extent of the cold gas was significantly larger than the pre-array estimates. This mattered for multiple reasons. A larger cold zone meant a larger total mass in the outflow. More mass meant more energy required to explain the outflow velocity. That made the single-star explanation even less plausible and the merger explanation even more necessary. It also mattered for the temperature record. The cold zone was real. The temperature was confirmed, but it was bigger than anyone had appreciated. The title of coldest natural object in the universe applied to a region far larger than the original measurements implied. The cosmic refrigerator was not a small cold patch. It was an enormous cold envelope, spanning distances that dwarfed our solar system many times over. The shape of the nebula in the new maps was also more detailed than before. The two lobes, the hourglass structure, showed hollow cavities inside. The gas was concentrated along the walls of the lobes, with emptier interiors. This hollow structure came from the way the outflow had been shaped by the dense dust disk around the central star. The disk blocked gas from escaping sideways. The gas funneled out along the poles of the star, creating the two elongated lobes rather than a simple expanding sphere. The disk itself showed up in the maps as a compact source of millimeter wave emission at the center of the nebula. Dense, large dust grains were concentrated there. They were left over from the merger event, material that had not been blown outward and instead settled into a disk around the collapsed core. These findings deepened the picture significantly. The merger created both the cold outflow and the dust disk that shaped it, two products of the same catastrophic event, working together to produce the unique structure visible in the sky today. But the most unexpected finding from the new maps was not about the cold, it was about warmth. At the outer edges of the nebula, beyond the central cold zone, the temperature was rising. The edges were warming up, and the reason they were warming introduced a clock into the story of the coldest place in the universe. The discovery came as a surprise to the team analyzing the data from the array's mapping of the outer nebula. They had expected the cold region to be relatively uniform, with near absolute zero temperatures throughout. What the data showed instead was patchwork. In the outer fringes of the cold outflow, some regions were showing signs of warming. The gas in those areas was emitting faint signals where before it had only been absorbing. Something was putting heat back into the outer cloud. This warming is confirmed by the observations, and scientists believe they understand what is driving it, though the full process involves some physics that was not initially predicted for this object. Here is what appears to be happening. The gas in the cold outflow is not perfectly transparent to light. Dust grains mixed into the gas can absorb photons, which are individual packets of light. When a photon is absorbed by a dust grain, it can knock an electron loose from the grain's surface. That electron carries away kinetic energy. Kinetic energy is heat, so absorbing light from the central star releases a small burst of warmth into the surrounding gas. This process is called the photoelectric effect. Scientists might recognize the name because it was explained by Albert Einstein in 1905, and it became one of the early foundations of quantum theory. In that context, it described electrons being knocked out of metal surfaces by light. The same principle operates at the surface of dust grains in a nebula. In the inner, densest regions of the cold outflow, the dust concentration is high enough that the warming effect is swamped by the cooling from rapid expansion. The cooling wins. The inner regions stay cold, but in the outer reaches, where the gas has expanded and thinned, the dust concentration drops and the expansion rate slows. The cooling is no longer as aggressive, and the warming from the photoelectric effect, though small, is now winning. The outer edges of the Boomerang Nebula are warming up, slowly, a fraction of a degree, still colder than the cosmic background in some patches. But the trend is clear. The cold is retreating inward. This finding fundamentally changes how scientists view the nebula's future. The cold zone is not stable. The record-breaking temperature is not permanent. The outer gas will continue warming over time. Eventually, the warming will penetrate inward. The unique conditions that make the Boomerang Nebula the coldest natural object in the universe are fading. The cloud is moving toward thermal equilibrium with the surrounding universe. A cosmic record held for 1,500 years in physical time is already beginning to slip, and the timescale over which it slips completely introduces a new element into the story. The coldest place in the universe may not hold that title for much longer. In astronomical terms, the rewarming of the outer Boomerang Nebula is a small effect, a fraction of a degree measured across enormous distances. But the physics behind it reaches into some of the most important work in modern science. When scientists first worked out why the outer edges of the nebula were warming, they had to trace the energy pathway carefully. The central star, collapsing and slowly heating up as it shrinks toward a white dwarf, still radiates light. That light moves outward through the cloud. When it reaches the outer regions of the outflow, it strikes dust grains. A dust grain in a nebula is tiny, far smaller than anything you could see. A speck of material, often silicate or carbon-based, floating in the gas. Normally, a dust grain absorbs a photon and re-emits it as heat, which warms the surrounding gas a little. The photoelectric effect goes further. It can strip electrons directly from the grain's surface. Those electrons then collide with gas molecules and transfer their energy as heat. The gas warms. In the inner regions of the cloud, where the gas density is higher, there are more cooling collisions happening. The gas is expanding rapidly there. The energy added by the photoelectric effect is tiny compared to the energy removed by expansion. The inner cold zone stays cold. Further out, the gas has expanded into a lower density, fewer collisions. The expansion is slower because the gas has already spread. The photoelectric warming now tips the balance. Small as it is, it wins over the weakened cooling. Scientists had predicted that something like this would eventually happen to the Boomerang Nebula. As the nebula ages and the central star slowly brightens, more ultraviolet radiation leaks out and accelerates the photoelectric heating. The warming progresses inward over time, eating into the cold zone from the outside in. There is a deeper implication here. The Boomerang Nebula is being studied precisely because it exists at such an extreme edge of what physics allows in nature. The cold is almost at absolute zero. The conditions are barely stable, and what scientists are watching in the outer edges is the universe pulling the temperature back toward equilibrium. The second law of thermodynamics at work. Entropy increasing. Systems moving from extreme order to disorder. From extreme cold to average warmth. No physical system can hold a record-breaking state forever. Everything tends toward balance. The Boomerang Nebula is not immune to that tendency. It is just fighting it on a grand scale, with 3 solar masses of expanding gas, for a window of time measured in thousands of years. The dust disk at the center is also playing a role in shaping which parts of the cloud warm and which stay cold longer. The disk shields some regions of the inner cloud from direct starlight, slowing the photoelectric heating there. The geometry of the outflow, the hollow lobes, and the thick disk determines the pattern of warming across the cloud. Scientists are now watching a process play out in real time, in astronomical terms. A record being broken, slowly, by the basic laws of physics, and it raises the most personal question in the whole story of the Boomerang Nebula. What does this mean for what comes next, for the star, for the cloud, and eventually for our own sun? The Boomerang Nebula has been in its current cold state for roughly 1,500 years. That is the estimated time since the merger event, since the companion star plunged into the giant and triggered the massive outflow. 1,500 years of continuous expansion, continuous cooling, continuous record-breaking temperature. In human terms, 1,500 years is enormous. Civilizations rose and fell in that span. The Roman Empire collapsed. The Renaissance happened. Multiple centuries of history unfolded. 1,500 years feels long. In stellar terms, it is a blink. Stars live for billions of years. Even the violent late stages of stellar death, the red giant phase, the mass loss episode, the planetary nebula glow, last tens of thousands to hundreds of thousands of years. The brief window during which a pre-planetary nebula can maintain temperatures below the cosmic background is far shorter than any of those phases. Scientists estimate that the cold zone of the Boomerang Nebula will persist for perhaps a few thousand more years before the warming penetrates inward and the temperature climbs above the cosmic background. After that, the nebula will enter the planetary nebula phase. The central star will heat up enough to start ionizing the surrounding gas. The cloud will begin to glow. At that point, the cosmic refrigerator shuts off. The temperatures will rise toward values typical of planetary nebulae, which are much warmer. The record will end. The entire window of extreme cold, from the merger event to the end of the sub-background phase, spans perhaps a few thousand years total. Against the billions of years of the star's life, that window is less than a fraction of a second on a 24-hour clock scaled to the star's lifetime. This makes the Boomerang Nebula an almost impossibly rare observation target. Catching a star in this specific phase requires pointing a telescope at the right patch of sky during the right few thousand-year window. The galaxy contains roughly 400 billion stars. Only a tiny fraction are the right mass to produce this outcome. Of those, only a fraction have had a companion star merge with them. Of those, most are outside the narrow window of extreme cold. Scientists suspect there may be other objects like the Boomerang Nebula hidden in the galaxy. Some may be colder, some may be older and already warming. Most would be too faint or too distant to detect with current instruments. The Boomerang Nebula came to attention partly through luck, a quiet survey of the southern sky in 1980 that happened to catch a faint boomerang shape at exactly the right moment in its history. The universe is full of extreme events that happen once and leave no record. The Boomerang Nebula is one we happen to catch in progress. And that timing is what allows the next question to be asked. What will become of the gas after the cold is gone? The Boomerang Nebula is unusual. The companion merger makes it extreme. The temperature makes it a record holder. But underneath those extremes, it is still telling the basic story of how a sun-like star dies. And that story belongs to our own sun as well. Our sun is about 4.5 billion years old. It has roughly 5 billion years of hydrogen fuel left. During that time, it will continue doing what it has done since the solar system formed, fusing hydrogen in its core, radiating light, holding the planets in orbit, steady, reliable, enormous and ancient, but not visibly changing from year to year. Then, in about 5 billion years, the hydrogen at the core runs out. The core begins to shrink. As it shrinks, it heats. The outer layers of the sun respond to that heat and start expanding. The sun swells into a red giant. It expands to perhaps 200 times its current size. Mercury will be swallowed. Venus will be swallowed. Earth's fate is less certain in the models, but the surface will be scorched to temperatures that make life impossible long before the sun reaches its maximum size. The oceans will evaporate. The atmosphere will strip away. After spending roughly 1 billion years as a red giant, the the sun will shed its outer layers. Gas and dust will expand outward into a glowing shell, a planetary nebula lit by ultraviolet radiation from the hot, collapsing core. The shell will glow for tens of thousands of years, then fade. What remains at the center will be the core, a white dwarf, roughly the size of Earth but containing most of the sun's remaining mass, dense enough that a teaspoon of its material would weigh several tons. Over billions of years, the white dwarf will cool, slowly releasing heat into space, fading from white to yellow to orange to red, and eventually going dark, a cold, dead remnant called a black dwarf. Though the universe is not yet old enough for any star to have reached that final stage, the Boomerang Nebula's central star is currently on this same path, already collapsed toward a white dwarf, already shed its outer layers. Except the companion merger made its death far more violent, far colder, and far more extreme than our sun's death will be. Our sun may not have a companion star to merge with. It is a single star. Its death will be quieter, a gradual expansion, a peaceful, if enormous planetary nebula, a gentle fade to a white dwarf. The Boomerang Nebula shows what happens when that process gets violently interrupted by a second star. Both paths end in the same place, a cold, dense remnant, and the gas blown outward from both will eventually mix into the interstellar medium, recycled into new stars, new planets. The atoms in the Boomerang Nebula's outflow will one day become part of other solar systems. Some of them may end up in planets, some may end up in life. That is an enormous thought. But the story of how the cold itself works, and what humans have done to explore temperatures just like it here on Earth, is stranger still. The question sounds almost simple. Could we, in a laboratory, cool something to the same temperature as the Boomerang Nebula, 1 degree above absolute zero? The answer is yes. Laboratories reached that temperature decades ago. In fact, by the 1990s, physics labs around the world were already achieving temperatures far colder than 1 degree above absolute zero, using techniques that required serious engineering but had become well established: liquid helium cooling, magnetic traps, dilution refrigerators. These tools could push small samples of matter well below 1 degree. The more interesting question is what matter does at those temperatures. At room temperature, matter behaves according to the rules that govern everyday life. Water flows. Metal conducts electricity with some resistance. Gas fills whatever container holds it. The atoms are moving fast enough that quantum effects, the strange rules governing very small things, are completely washed out by thermal noise. As you cool matter toward absolute zero, something shifts. The atoms slow, the thermal noise fades, and quantum mechanics starts to dominate the behavior of the material. The first strange thing you notice is that some materials stop resisting electricity entirely. At normal temperatures, electrons moving through a metal bump into atoms and lose energy. That lost energy becomes heat. You can feel it in a phone charger getting warm. At very low temperatures, in certain materials, electrons start moving through the material in a coordinated way, pairing up and flowing without any collisions at all. Zero resistance, perfect conduction. This is called superconductivity, and it appears in many materials when cooled below a critical temperature. A superconducting current, once started, keeps flowing forever with no power source needed. Scientists have run currents in superconducting loops for over a year with no measurable decay. The electricity just keeps going, in a circle, with nothing driving it. Then there are superfluids. When liquid helium is cooled below a certain temperature, it stops behaving like a normal liquid. It develops zero viscosity. It flows without friction. It climbs up the walls of its container. It can seep through gaps so small that no normal liquid would pass through. It forms thin films that spread across every surface. A superfluid poured into a cup will slowly creep up the sides and drip out the bottom, entirely under its own initiative, defying the way you expect liquids to behave. Both superconductivity and superfluidity arise from quantum mechanics taking over when thermal noise is removed. The atoms or electrons start acting in concert, behaving as a unified quantum system rather than a crowd of individuals. These are not exotic things observed only in distant nebulae. They are phenomena that humanity has harnessed. Superconductors are inside every hospital MRI machine. They run the magnets that steer particles in accelerators. They are central to the next generation of quantum computers. The extreme cold of the Boomerang Nebula, applied in a lab, has already changed medicine and physics and will change computing. But getting to temperatures far below 1 degree, approaching absolute zero itself, required a new setting. One that only became available when humanity launched something into orbit. In 1995, when Sahai and Nyman confirmed the Boomerang Nebula's temperature, the 1 degree mark was roughly at the edge of what advanced physics labs could achieve. The nebula and the best human technology were sitting at a similar threshold. Within a few years, that changed. Physicists developed techniques to push far below 1 degree. The key tools were laser cooling, magnetic trapping, and evaporative cooling. Laser cooling works by firing photons at atoms from specific directions. Each photon that hits an atom slows it slightly. Enough photons from enough directions, and the atoms slow to a crawl. Magnetic traps hold the cooled atoms in place without touching them. Evaporative cooling then removes the warmest atoms from the trap, the same way a hot cup of coffee cools faster as steam carries away the hottest water molecules. What remains is a colder, smaller sample. Using these methods in sequence, labs cooled atoms to millionths of a degree above absolute zero, then billionths. The Boomerang Nebula's 1 degree was far behind. There was a problem, though. The colder atoms get, the harder gravity makes the experiment. On Earth, even an extremely cold cloud of atoms falls. Gravity pulls it down. The cloud hits the bottom of the experimental chamber, and the experiment ends. For brief flashes of extreme cold, a fraction of a second at most, gravity kills the observation. You cannot study the behavior of ultra-cold atoms for long before the cloud drops. Scientists found a solution. Remove gravity. Go to space. In 2018, NASA launched a device called the Cold Atom Laboratory to the International Space Station. It is roughly the size of a mini-fridge. It carries inside it the equipment needed to cool atoms to temperatures near absolute zero. Lasers, magnetic traps, vacuum chambers, electronics, all of it remote-controlled from the ground. In the microgravity of low Earth orbit, the falling problem disappears. A cold cloud of atoms released from its trap does not drop, it floats. Scientists can watch it for seconds instead of fractions of a second. They can cool it further. They can study how it behaves without the experiment ending prematurely. The results changed what was achievable. Temperatures below 100 millionths of a degree above absolute zero became routine in orbit, and the stage was set for colder still. But the ultimate record, the temperature that made headlines and shocked physicists, did not come from space. It came from a tower in Germany, and what those scientists did to achieve it was something nobody had tried before. Before getting to the German tower and the coldest temperature ever measured, you need to understand what happens to matter at those extremes. Because at the temperatures scientists are chasing near absolute zero, matter does something genuinely strange. It enters a new state that nobody predicted from ordinary physics. Everybody learns the 3 states of matter early: solid, liquid, gas. Then there is plasma, which most people learn about later. But at ultra-cold temperatures, a 5th state appears. It was predicted mathematically in the 1920s by Albert Einstein and an Indian physicist named Satyendra Nath Bose. For decades, it stayed purely theoretical. Then in 1995, 2 physicists at a lab in Colorado actually created it. It is called a Bose-Einstein condensate. Here is what happens. At room temperature, atoms in a gas are all behaving individually. Each atom has its own velocity, its own position, its own separate identity. The crowd of atoms is chaotic. When you cool the gas, atoms slow down. At some point, Close enough to absolute zero, something shifts. Atoms in quantum mechanics are described by waves. The position and properties of an atom are spread out in a probability wave. At high temperatures, those waves are tiny and separate. Each atom is its own wave, totally distinct from its neighbors. But as the temperature drops towards zero, the waves spread out. They grow larger, and eventually, all the atoms in the gas are in exactly the same quantum state. Their waves overlap completely. All the atoms merge into a single quantum wave, acting as one giant atom rather than a crowd of individuals. When this happens, the gas stops being a collection of particles. It becomes a single quantum entity. Strange things follow from this. The whole cloud of atoms starts moving together, acting as one body. Interference patterns appear. The cloud exhibits wave-like behavior visible at a scale you could almost photograph. Quantum effects that usually require instruments to detect at the atomic level become visible at sizes of millimeters or even centimeters. Physicists love this state because it makes quantum mechanics visible in a way that nothing else does. The subtle, invisible rules that govern atoms and electrons suddenly manifest at a scale you can observe directly. It is like getting a magnifying glass for the quantum world. And the key to creating a Bose-Einstein condensate is temperature. You need to cool the gas close enough to absolute zero that the quantum waves spread out and overlap. The cooler you get, the more perfect the condensate. Getting colder is a way of seeing more of quantum mechanics. The Cold Atom Laboratory on the space station creates these condensates in orbit. In the absence of gravity, they last longer and cool further than any on Earth. Scientists can study how the condensate behaves in microgravity, learning things about quantum mechanics that ground-based experiments cannot reveal. But even beyond the condensate, there was a record waiting to be broken, and the German team chasing it found an unexpected way to get there. The Cold Atom Laboratory sits in the United States Science Module of the International Space Station, orbiting Earth at roughly 250 miles up. Astronauts pass by it on their way to other experiments. From outside, it looks like a rack of electronics, the kind you might find in a server room. Inside, it contains one of the most sophisticated cold physics experiments ever built. The lab works by a combination of tricks. First, a cloud of rubidium atoms is loaded into the vacuum chamber inside the device. Rubidium is a soft, silvery metal that, when heated into a gas, produces atoms that respond well to laser cooling. Scientists fire carefully tuned laser beams at the atoms from multiple directions. Each photon that strikes an atom slows it. 6 beams, 2 from each axis, slow the atoms in every direction at once. The atom cloud drops in temperature rapidly, from room temperature to a fraction of a degree above absolute zero in a few seconds of laser firing. But the lasers cannot get all the way to the coldest temperatures on their own. After the laser step, a magnetic trap holds the cooled atoms in place. Radio waves are then used to remove the warmest atoms from the trap. The remaining atoms, the coldest ones, settle lower in energy. The temperature drops further. The whole process, from room temperature gas to an ultra-cold Bose-Einstein condensate, takes a matter of seconds. And it can be run repeatedly, automatically, controlled by scientists on the ground who monitor the results in real time. In microgravity, the condensate released from the trap does not fall. It floats. Scientists can watch it expand slowly, observe its interference patterns, and measure its properties for 10 times longer than a comparable experiment on Earth would allow before gravity ends the observation. That extended observation time has already produced science that would have been impossible on the ground. The Cold Atom Laboratory is also preparing for upgrades. A next-generation system planned for the station will cool atoms to 1/1,000,000th of a degree above absolute zero. 1/1,000,000th. The Boomerang Nebula, sitting at roughly 1 degree, would be 1 trillion times warmer than the planned experimental temperature. A natural object in deep space versus a physics experiment in orbit. The experiment, when it runs, will win by an almost unimaginable margin. But there is still the matter of the German record, the one set with a tower, a magnetic field, and a calculated fall. The gap between what the space station achieves and what that experiment achieved reveals something important about the physics of extreme cold, and why the last fraction of a degree above absolute zero is so much harder to reach than everything that came before it. Gravity is the enemy of extreme cold experiments. The problem is not the weight of the equipment. The problem is what gravity does to the atoms themselves. When scientists cool a cloud of atoms on Earth and then release it from the magnetic trap, the cloud begins to expand. Expanding gas gets colder. The expansion drives the temperature lower. But expansion on Earth is not free. Gravity pulls every atom in the cloud downward. The cloud does not expand evenly in all directions. It falls while expanding. The atoms at the bottom of the cloud move slightly faster than the atoms at the top, not because of thermal motion, but because of gravity. That asymmetry adds an energy difference across the cloud. It limits how cold the effective temperature can be measured to be. On the space station, there is no preferred direction of fall. All parts of the cloud and the entire station are falling together around Earth. In that environment, releasing the atoms from their trap allows the cloud to expand in all directions equally. A perfect sphere of expansion. No asymmetry, no gravity-induced energy difference. The measurements become cleaner. The effective temperature drops further. This is why the Cold Atom Laboratory in orbit achieves temperatures that labs on Earth cannot match for sustained periods. The microgravity environment removes the main obstacle, but the German team wanted to go further still. And their approach was to simulate microgravity on Earth for just long enough to take a measurement. In the city of Bremen, there is a drop tower. The tower stands 393 feet tall. At the top, scientists prepared a sealed experiment chamber containing a cloud of atoms, cooled to a few billionths of a degree above absolute zero. Then they dropped the entire chamber. The chamber fell 393 feet under gravity, but because everything inside the chamber was falling at the same rate as the chamber itself, the atoms inside experienced effective weightlessness. No preferred direction of pull, no asymmetry. During that fall, while the chamber plummeted toward the cushioned landing area at the bottom of the tower, the scientists switched a magnetic field on and off in a carefully timed pattern. The magnetic pulses squeezed and released the atomic cloud in a specific way. Each squeeze-release cycle removed energy from the cloud. The temperature dropped. The fall lasted only about 9 seconds. But 9 seconds of effective weightlessness was enough. At the end of the fall, the temperature in the cloud reached 38 trillionths of a degree above absolute zero, the coldest temperature ever recorded anywhere. The Boomerang Nebula, the coldest natural object in the universe, sits at roughly 1 degree. The record from the Bremen Tower sits at 38 trillionths of a degree. The lab beat nature by a factor of roughly 26 billion. But holding that record and making it last more than 9 seconds is an entirely different challenge. 38 trillionths of a degree, written as a fraction, that is 38 divided by 1 trillion, a number so small that writing it requires a decimal point followed by 11 zeros before the 38 appears. The cold achieved in the Bremen Drop Tower experiment was not a mistake, not a calibration error. It was real, verified, and published in the journal Science. A German and French research team had pushed matter closer to absolute zero than any previous measurement in history. To understand what 38 trillionths means, consider the steps down from everyday temperatures. Room temperature sits at roughly 70 degrees Fahrenheit. Liquid nitrogen, used to flash freeze things in cooking demonstrations, is almost 300 degrees colder. Liquid helium, used to cool medical scanning machines and particle accelerators, is colder still, near 4 degrees above absolute zero. The Boomerang Nebula is at 1 degree. The Cold Atom Laboratory on the space station works at 1/10 billionth of a degree. The Bremen record reached 38 trillionths. Each step down in that chain requires more sophisticated technology than the last. The gap between 1 degree and 1/10 billionth is smaller in absolute terms than the gap between room temperature and 1 degree. But achieving each new step takes years of engineering refinement. The physics becomes progressively more sensitive. Tiny vibrations in the equipment, stray magnetic fields, even the electromagnetic radiation from nearby electronics can add energy to the atoms and warm them. Everything that can introduce heat must be eliminated. The Bose-Einstein condensate used in the Bremen experiment was made from rubidium atoms, the same type used in the cold atom laboratory, cooled to a few billionths of a degree with lasers and magnetic traps, then launched into freefall in the drop tower. The magnetic field pulses during the fall. The specific timed pattern of squeezing and releasing the atoms drove the temperature down further than any other method had managed. At 38 trillionths of a degree, the rubidium cloud was in a state that has no parallel in nature. Every atom in it was in exactly the same quantum state. The cloud behaved as a single entity, a quantum wave spanning a region large enough to see. The rules governing individual subatomic particles were operating at a scale visible to the eye. What scientists hoped to learn from studying matter at those temperatures was not just the temperature record. The condensate at extreme cold is sensitive to tiny forces in ways that warmer matter cannot be. Physicists can use it as a measurement tool, an instrument to detect the faintest gravitational variations, the weakest electromagnetic fields, possibly even effects from physics that has not yet been discovered. Every step closer to absolute zero opens a window onto phenomena that have been invisible. But the record lasted 9 seconds. The tower provided only 9 seconds of freefall. Then the chamber landed. The atoms were no longer in effective weightlessness. The measurement ended. The record stands, but the window was 9 seconds wide. You have already heard about superconductors and superfluids and Bose-Einstein condensates, but the specific behaviors of matter near absolute zero deserve a closer look, because they are not just scientific curiosities. They are genuinely alien compared to everything matter does at everyday temperatures. Start with superfluid helium. Liquid helium cooled below a specific temperature, around 4 degrees above absolute zero, becomes a superfluid. It has zero viscosity. Zero is not a small number here. It is genuinely exactly zero. No friction at all. No resistance to flow. Pour a normal liquid into a cup and it stays there. The sides of the cup exert friction. Gravity holds the liquid down. The liquid sits still. Pour superfluid helium into a cup and it starts climbing. A thin film of superfluid forms on the inside wall of the cup. The film spreads upward. The superfluid has zero friction and therefore no resistance to climbing the wall. It creeps up the side, over the rim, and drips down the outside. A cup of superfluid helium will empty itself by climbing out. If you stir superfluid helium and then leave it alone, it keeps spinning. No friction means nothing slows the rotation. The liquid circulates indefinitely, forming vortices, tiny spinning tubes of fluid that can persist essentially forever once started. Scientists call these quantum vortices. They form in patterns determined by quantum mechanics, not by the random turbulence of normal fluids. Superconductors are stranger still in some ways. Below a critical temperature, certain materials expel all magnetic fields from their interior. This is called the Meissner effect. A superconductor placed near a magnet will push the magnet away. The superconductor actively repels the magnetic field. This is not magnetism in the ordinary sense. It is a quantum effect, a consequence of the electrons inside the material moving in a coordinated collective state that rejects external magnetic influence. The levitation this produces is real and measurable. A small magnet floating above a superconductor, held in place by the Meissner effect, will stay there indefinitely as long as the material stays cold. No energy input needed. The floating is sustained by quantum mechanics. Both superfluidity and superconductivity emerge from the same underlying physics. In both cases, the relevant particles, atoms in a superfluid, electron pairs in a superconductor, enter a collective quantum state. They stop being individuals. They all do the same thing at the same time. That collective behavior produces properties that individual particles cannot have. Zero viscosity, zero resistance. The Bose-Einstein condensate takes this further. In a condensate, every atom is in exactly the same quantum state, more completely than in a superfluid or superconductor. The whole cloud acts as one entity, wave-like, coherent, sensitive to the faintest external influences. All of this behavior traces back to cold. Remove heat, remove thermal noise, and the quantum rules that govern atoms at any temperature become the dominant influence on how matter behaves. The everyday world disappears. A quantum world takes its place. And this quantum world at extreme cold holds the key to technologies that will shape the coming decades. Here is the paradox sitting at the center of the whole story. Human laboratories have built temperatures almost 26 billion times colder than the Boomerang Nebula. The best lab in the world, using the most sophisticated equipment ever designed for cold physics, reached 38 trillionths of a degree above absolute zero. The nebula sits at roughly 1 degree, and yet the nebula has held its temperature for 1,500 years. The lab record lasted 9 seconds. How is that possible? How can a dying star in deep space, with no lasers and no magnetic traps, maintain near absolute zero temperatures for a millennium and a half, while humanity's finest experiment runs for less than the time it takes to yawn? The answer is volume and isolation. The Boomerang Nebula is enormous. The cold region spans distances measurable in light years. The total mass of gas in the cold zone is more than 3 times the mass of the Sunday. When something that massive is that cold, warming it back up takes a colossal amount of energy. The cosmic microwave background is there, flowing in from every direction, trying to add warmth. But 3 solar masses of gas can absorb a lot of warming energy before the temperature rises noticeably. The cold zone is so vast that the universe takes a very long time to pull it back to equilibrium. The lab condensate, in contrast, holds a tiny number of atoms, 100,000 rubidium atoms in the Bremen experiment. 100,000 sounds like a lot, but it is an almost immeasurably small amount of mass. The slightest vibration, a single stray photon, a tiny fluctuation in the magnetic field, any of these adds enough energy to warm 100,000 atoms out of their extreme cold state instantly. Holding the record temperature requires isolating those atoms from every possible energy source, and isolation on Earth is imperfect. In space, the nebula is also isolated in a sense. The background warmth flowing in is tiny and spread over an enormous area. The distance from the nearest warm star is vast. The energy density of the environment is low, but the key difference is mass. 3 solar masses of nearly absolute zero gas is an almost inexhaustible cold reservoir. 100,000 atoms of rubidium are trivially easy to warm. Mass wins. The cold of the nebula is not deeper, but it is far more robust. This is also why the end of the nebula's cold period is measured in thousands of years rather than seconds. Warming it back up is a slow process precisely because there is so much of it. The photoelectric heating from dust grains, the slow leakage of the cosmic background warmth. These processes are tiny compared to the thermal mass of the cold gas. They nibble at the edges. Centuries pass before a measurable amount of warming reaches inward. The lab and the nebula are opposites in this way. The lab goes deeper, the nebula goes longer. Together, they bracket the full landscape of what cold means at the extreme limits of physics. And those extremes, both in space and in the lab, point toward a destination that the entire universe is moving toward. Slowly, irreversibly, across timescales that make everything discussed so far look brief. The universe is getting colder. It has been getting colder since the moment of the Big Bang. The expansion of space stretches the wavelengths of light. Longer wavelengths carry less energy. Lower energy means lower temperature. The background temperature of the universe, currently at 2.7 degrees above absolute zero, was billions of degrees in the first seconds of existence. Over 14 billion years of expansion, it has cooled to that faint cosmic glow, and it keeps cooling. The universe will not stop expanding. Measurements over the past few decades, using the light from distant exploding stars, showed something unexpected. The expansion of the universe is accelerating. A mysterious pressure-filling space, which scientists call dark energy, is pushing galaxies apart faster and faster over time. The expansion will not slow down, it will speed up. As galaxies accelerate away from each other, they eventually move so fast that light from distant ones can no longer reach us. 1 trillion years from now, the Milky Way and its nearest neighbors will have merged into a single galaxy. Every other galaxy will have receded beyond the point where its light can ever reach us again. The sky will go dark, except for the combined light of our local merger. Stars will keep forming for roughly 100 trillion years after the present, burning through the available gas in galaxies. One by one, they will exhaust their fuel. They will die. Some will become white dwarfs, cooling over vast timescales. Some will become neutron stars. The largest will leave black holes. After all the stars burn out, the universe enters what cosmologists call the degenerate era. Galaxies are replaced by drifting clusters of dead stars and black holes. Slowly, over timescales that dwarf the current age of the universe, many times over, black holes evaporate. Subatomic particles may eventually decay. All structure dissolves. The background temperature of the universe keeps dropping throughout all of this. It follows the expansion of space. As space grows larger, the photons in the cosmic background stretch further. Their energy drops further, and the temperature falls toward absolute zero. The universe's final state, according to the best current models, is called the heat death. All matter and energy spread evenly across an incomprehensibly vast space. No temperature gradients, no hot spots, no cold spots. Everything at the same temperature, hovering just above absolute zero. No processes possible, no stars, no light, no chemistry, no life. Just a vast, cold, dark, almost perfectly uniform expanse. The Boomerang Nebula sits at 1 degree above absolute zero today. The universe's ultimate temperature will be closer still to the floor. The nebula is not special in its destination. It is simply ahead of schedule, an early preview of where everything ends up. In the arc from the Big Bang's billions of degrees to the heat deaths near absolute zero, the Boomerang Nebula is a cold blip, an extreme point on a curve that the universe is slowly tracing downward. Everything cools. The nebula is just cooling faster than most things. And what it reveals about the physics of that cooling, about star death and mergers and expansion and temperature, makes it a window into the cold fate of everything. One more thing remains to be said about what that window means. The Boomerang Nebula started as a faint shape in an astronomer's catalogue, noticed in Australia in 1980 and largely forgotten. It became the coldest known natural object in the universe when a radio telescope in Chile read its temperature in 1995. It stayed mysterious for 22 more years while scientists tried to explain how a single dying star could do what the data showed. And in 2017, the answer came. It was not a single star. It was 2 stars. One swallowed the other. The merger drove the outflow. The outflow drove the cold. Along the way, the nebula taught something broader than its own story. It showed that the universe creates extreme conditions in places you would not expect. A quiet corner of our galaxy, unspectacular in most ways, became the coldest place in the observable universe. Through a chain of events, that started billions of years ago when two stars were born close enough to eventually find each other. It showed that the death of stars is more violent and more varied than simple models suggest. Binary systems, star mergers, companion infall, common envelope evolution. These processes shape the deaths of a significant fraction of all stars in the galaxy. The Boomerang Nebula is an extreme example, but the underlying process is common. Many of the stars visible in the sky at night are binary or multiple systems. A large fraction of them will interact with their companions at some point in their lives. Some will produce events similar to the boomerang, though perhaps less extreme. It showed that the laws of thermodynamics do not bend, but they can be stretched. The Boomerang Nebula reaches temperatures that the surrounding universe cannot sustain without extraordinary energy input. The expansion of the outflow provides that input for a brief window of thousands of years. Eventually, the laws win back, the warming creeps in, the temperature rises, the record ends. It showed that human technology can surpass nature at its most extreme, at least briefly. Labs on Earth and on the International Space Station now create temperatures far colder than the Boomerang Nebula, though only for seconds or minutes before warmth floods back in. The science those labs produce, superconductive materials, quantum sensors, Bose-Einstein condensates, is already reshaping medicine, computing, and physics. And it showed something about the long-term story of the cosmos. Everything cools. Stars burn and die. Galaxies dim and disperse. The background temperature of the universe falls toward absolute zero over timescales that human minds struggle to hold. The Boomerang Nebula is a local, temporary, dramatic version of that universal trend. A dying star, through an accidental collision with its companion, produced the coldest natural structure in the known universe, and in doing so, it handed scientists a rare and precise instrument for understanding what happens to matter at the edge of all possible cold. 5,000 light-years away, the gas is still expanding. The outer edges are slowly warming. The inner cold is still intact. 1,500 years of record holding, with a few thousand more remaining. A blink in the life of the galaxy. An enormous window for science. The coldest place in the universe is a frozen scar left by a star that swallowed its partner. And the closer we look, the more it tells us about the cold that waits for all of us at the end of everything.